Hi everyone. So this week I'm doing Stark 101. What I'm going to do next is going to give you like a condensed version of Stark 101 and then with an example. So probably will be too easy for most of you guys, but I'm gonna start. And this is going to focus on the prover side of Stark. So I'm gonna cover a couple steps. So we're gonna start from a statement. And then computation stress. And the extension. And then we're going to look at the composition polynomial. And then Frey commitment. And then query. So the example we're going to look at today is there is a number x, so statement. So there is a number x such that if a0 equals to 1, a1 equals to x. So this is a Fibonacci sequence example. And the 1022 elements here is going to be 2, 3, 3, 8, sorry, 7, 7, 5, 0, 5, 7. So we basically wanted to prove this. And this is a number after molding a prime. Sorry, let me put it here. Wow. So this is a statement we're going to prove and then use as an example today. So let's start with computation trace and extension. So when we talk about computation trace, we need to talk about LDE. LDE stands for low degree extension, and LDE is actually composed of 3 steps. It's you can first get a you first get generate input. And then you interpolate the input and then get a polynomial. Then finally you extend it. So this is to add redundancy to the data we have. So for in this example, we have A0, A1, dot, 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 and this is going to be the trace that we're using. So input, we're going to be A0, A1 to A1022, and this is the trace. And when we get the trace, then now we map it with elements in the groups. So we use 1, G squared, G1022. And if we visualize it, it will look like something like, ooh. If we visualize it, it will look like something like this. So this is G, and then we try to map A0, A1, like there's a couple of dots there, and then we interpolate this polynomial and then get something like, okay, I'm drawing randomly. So now we get a polynomial like this, and this is FGI equals AI. And now we extend it, and how we extend it is that we pick a larger evaluation domain, and then we basically make more like dots in between. So we pick and here we can use the Reed-Solomon code word. So what we'll get is that we choose the xi. Oh my God. So notice that how the original points we have is at thousands, and then now we expanded to 8K. And then we use this point to calculate the result, right? So we will get the f of omega h, f of omega h squared, and until the f of omega h 8K-ish results. And then after we get all of this, we can put this into a Merkle tree. So basically, so we compute. Okay, I'm just going to. So we compute the hash. So when the prover sends something to the verifier, instead of sending like the all 8K result, we can just send a single hash that will like concludes everything. Okay, so this is the intuition behind computation straits and extension. And now I'm going to talk about composition polynomial. So we see we have the state. Oh, I erased the statement. So the statement we wanted to prove is the Fibonacci sequence. And now for the composition polynomial, we start from looking at what constraint we have for A. So A is, I erased it, but we use it in a statement. We basically wanted to prove, let me put it again. So this is a Fibonacci. Not sure if I like make it correctly. But okay, so when we're looking at composition polynomial, we first look at what constraint we have on AN. So constraint. So first we know that we have to start with 1, right? So A0 equals to 1 is one of the constraints. And then the final value is this one. So the final value is also one of the constraints. And then the next constraint is basically saying that this sequence is computed correctly. And now we have the constraint on AN, but how do we like convert it into the constraint on F? So now we wanted to make it into constraints. So basically put it into polynomial. So now we have fx equals to 1 for x started with G0. And then fx should be the final number when when x is equals to this. And the last one is to make sure the computation sequence is correct. So. And for this one, this is for x where I is okay. So we now have this, and then we do the trick that we've seen a lot of times already. So basically, we wanted to prove that we divided, we fx like minus the result and divided by the x minus the root value, and it is still a polynomial. So with these three constraints, we can get three polynomial, which would be fx minus 1, and I'll just be lazy here. And then the final one, so g square x minus f gx square, sorry, minus fx square. So we get these three, and if all these constraints, like, if all these constraints, if we, how to say, sorry, if we match all these three constraints, then these three should all be polynomial. And now, instead of like verifying on these three, we use a composition to make it together. So composition polynomial is equals to this polynomial times alpha 0. Like this. So we make this into one single polynomial, and if this single polynomial is a polynomial, then these three are all polynomials. Okay, so now we have this, and then how do we prove that this is a polynomial? Now we're going to the next step, the FRI part. So in the FRI part, the intuition is that instead of proving the composition polynomial is a polynomial, we prove that it is close to polynomial of low degree. So in FRI algorithm, there's 3 steps, 4 actually, FRI. So first, it will receive a random beta. And then it will apply the FRI operator. Then it will commit to the result. And finally send the result. And these 3 steps, we're going to do it like in a loop. It's gonna be multiple times. So how it looks like is, remember we had this composition polynomial. And with the example I mentioned earlier, it's going to be of degree. It's less than 1024. So we have this, CP commitment. And what we're trying to do it here is we're trying to reduce the size of this thing we want to check. So here we will get a random number beta, and then we reduce the size to half, maybe a little bit shorter. And so we try to get the degree in half, and so on, until we get constant size, or the size that we think it's small enough for us to do the computation. And how this is done is what we call the FRI operator. And what FRI operator is actually, if we have a P0, like a polynomial 0, and then we separate the polynomial with the even coefficients, the even part and the odd part. And then we get a random beta. And now we basically rewrite this polynomial into something Py. And how it looks like with an example, I think it will be easier to understand it with an example. So let's say we have P0, 5x 5 times. Now we try to put it from P0 form into P1 form. So for GY, it's actually quite easy for this one. We just substitute x squared into y, right? So it's gonna be oh sorry, 3y squared plus 2y plus 3. And then for beta hy, we can first look at x squared. This will be easier. So when we look at it here, we just put it down. So this is the odd items. And then we put beta hy here. So it's going to be 5x squared, oh sorry, 5y squared, 7y, and 1. So you see how like the degree is shrunk into y in this way. So this is the intuition behind the FRI operator. And then now we can do like the commit and then send the result part. So I'm gonna talk about next is how the proof is like and what we're going to send in the end. So it's going to be the last part. Time's up. Okay. 2 more minutes. Is that okay? Yeah. So I'm gonna quickly talk through it. So now looking back, we have trace. The AN thing. And then we have the composition polynomial, CP. And then we have, so we do the Frey steps multiple times, and every time it's like half size of the original base. So and for the commitment, so remember how we can compute this into Merkle tree and then get the final hash, right? So we will have the trace root, and then the CP root. So basically, we get all the roots from all these computations. So and then when the prover wanted to prove the verifier that the computation is done correctly, other than the roots, it also has to show that the path it's done correctly, right? So it's also we need to send the path, and the path is we can get it from the Merkle tree. Okay, and so the computation of a Merkle tree path is log n size. Log n complexity, and the trace size we need to compute is also in log n. So together we will have log square of n complexity. Okay, and I think that's it.